Alright, hello everyone and welcome to our next video of Unit 8 for the AP Chemistry curriculum. We are going to be doing Lesson 8 and Lesson 9 in today's video. First, we're going to be focusing on the properties of buffers. So the key idea is that a buffer is a solution that resists changes in pH when small amounts of acid or base are added. You can think of a buffer like a chemical shock absorber. It prevents large swings in pH. This happens because a buffer contains relatively large amounts of both a weak acid and its conjugate base, or a weak base and its conjugate acid. When we add acid, meaning we add protons or H plus ions, the conjugate base reacts with that H plus and removes it from solution. On the other hand, when we add a base like OH minus, the weak acid in the buffer reacts with it and neutralizes it. Because these reactions are happening, the added base or acid doesn't significantly change the concentration of H plus in solution, so the pH stays relatively stable. A buffer is a solution that resists change in pH because it contains both a weak acid and its conjugate base, or a weak base and its conjugate acid. That pairing is what allows the solution to neutralize added acid or base. Now, when we're trying to identify whether something forms a buffer, you need to look for two things. The first is a conjugate acid-base pair, meaning they only differ by one proton. And the second thing is it does have to be a weak acid in its conjugate base or a weak base in its conjugate acid. So if you're looking at a conjugate acid-base pair like H2SO4 and HSO4 minus, H2SO4 or sulfuric acid is a strong acid, so that would not form a buffer. The pair OH minus and NH3 doesn't work either because they are not conjugates of each other and they don't differ by just one proton, which is what a conjugate is. The correct answer is our group on the right, which is acetic acid and acetate. That is a conjugate acid-base pair because it's only differing by a proton, and acetic acid is a weak acid, so that would form a buffer. Weak acids and weak bases only partially dissociate, which means they establish an equilibrium with their conjugate pairs. That equilibrium is what allows buffers to work because when we add H plus or OH minus, the system shifts to counteract that change and then maintain a relatively stable pH. On the other hand, strong acids and strong bases fully dissociate, so there's no equilibrium established, and because of that they can't respond to added acid or base and they don't form buffers. So let's apply that idea and look at the following four pairs and figure out if they will form buffers. Our first pair is sodium hydroxide and Na+. That is not going to form a buffer because NaOH is a strong base and Na+ is just a spectator ion, so it's not even a conjugate pair. NH3 and NH4NO3 will form a buffer because NH3 is a weak base and NH4 plus is the conjugate acid that comes from that. Our next group is CH3COOH, which is acetic acid, and calcium acetate. So because acetic acid and acetate is a conjugate pair and acetic acid is a weak acid, that will form a buffer. And then our last pairing is HI and I minus, and even though that is a conjugate acid-base pair, HI is a strong acid, so that would not form a buffer. So out of these four options, NH3 and ammonium nitrate would form a buffer, and acetic acid and calcium acetate would form a buffer. All right, so when we have a solution or a buffer that has a weak acid and its conjugate base, that is known as an acidic buffer. An acidic buffer is made from a weak acid and its salt, and that salt is going to contain the conjugate base. A really common example is going to be acetic acid and sodium acetate. The key idea here is that the salt dissolves completely and supplies a high concentration of the conjugate base, while the weak acid only partially dissociates, setting up that important equilibrium between the weak acid and its conjugate base. So let's look at this example here where we are neutralizing acetic acid with sodium hydroxide. And from here, I want to get our net ionic equation so that we can truly see what's happening at the particle level when we introduce an acid or base to this equilibrium. So because this is review from past units, I want you to pause the video and write out the complete ionic equation for this neutralization reaction. So if you remember from past lessons, when we have a weak acid or a weak base, that is not going to dissociate. So that is going to stay whole in our complete ionic equation. So acetic acid will remain together and not dissociate. And if we want to be a little more specific, I will add our states of matter in case you are practicing that. Then sodium hydroxide is a strong base. And remember, the definition of a strong acid or base is that it completely dissociates. So if we were writing the complete ionic equation, we would have Na plus and OH minus. Then we have sodium acetate. And sodium acetate is an ionic salt, which is dissolvable in water, and you should know that because it has sodium in it. So that is going to have acetate, CH3COO minus dissolved in water, and sodium ion dissolved in water. And then we have liquid water, which pure liquids do not dissociate into ions. So that is going to stay together like that. So this is what's called our complete ionic equation. Remember, the difference between a complete ionic equation and a net ionic equation is the removal of the spectator ions. So we can see here we only have one set of spectator ions, and that is sodium. So those will be removed, and for the net ionic equation, it will just be acetic acid plus hydroxide reacts to form, and this should be a double-headed arrow, acetate and water. Now, if you can go directly from the original equation to the net ionic equation, that is wonderful. I'm just showing you the pieces in case you ever have to do a complete ionic equation or identify the spectator ions on your AP chemistry exam. So now that we have our net ionic equation, we can really see the reacting species in this equilibrium equation. So remember, the whole purpose of a buffer, or the beauty of a buffer, I should say, is that when you add acid or base, it's going to respond to that stressor with Le Chatelier's principle, and it's going to shift the equilibrium to offset the change in pH. So in this specific equation, if we were to add a base to this reaction, we are increasing the concentration of OH minus, which is going to shift the equilibrium to the products to offset that change. Now, if we were to add an acid to this equilibrium, you would be adding H plus ions to the reaction, which means H plus is going to react with OH minus to form water, which means we are decreasing hydroxide, and the equilibrium is going to shift to the left. You can also think of it in a more basic way in terms of an acid and a base reacting with the weak acid and the conjugate base. So we know acetic acid is our weak acid and acetate is our conjugate base. So if we are to add base, then it is going to react with the weak acid and therefore make more products. So same concept, we're still shifting right if you want to think about it that way. Then with adding acid, we're going to be adding acid, which will react to our conjugate base to form more reactants, so therefore shifting left. So either way you think about it, it's still shifting the correct way. It just kind of depends on how you would like to approach the process. All right, and now let's talk about basic buffers. So basic buffer is made from a weak base and its salt, which provides the conjugate acid. A really common example in AP chemistry is ammonia and ammonium. Just like with acidic buffers, the salt is going to dissolve completely to provide a high concentration of your conjugate acid, while the weak base partially reacts with water, establishing that equilibrium with a buffer. So looking at this reaction, we can see we have a weak base, ammonia, reacting with a strong acid, hydrochloric acid, and it's going to form an ionic salt, ammonium chloride. Now let's go ahead and practice again getting our complete ionic equation for this reaction. We know that NH3 is a weak base, so that is not going to dissociate in our complete ionic equation. So it's just going to be NH3, and because it's a base, we know it's aqueous dissolved in water. Then we have hydrochloric acid, which is a strong acid, which means complete dissociation. So HCl will dissociate into H plus ions and Cl minus ions. And then we have ammonium chloride, which is an ionic salt, and because it has ammonium in it, we know that it's soluble. So that's going to dissolve into NH4 plus and Cl minus. So again, this is known as our complete ionic equation. And to get our net ionic equation, we're going to remove our spectator ions. In this case, those are the Cl minus ions. So for our net ionic equation, we will have NH3 or ammonia reacting with H plus ions to form ammonium. So again, we can think of this two ways. First, I'm going to be focusing on the thought process that includes looking at either the OH minus or the H plus, so in this case, the H plus. So if I were to add a base to this equilibrium, I'm adding OH minus, and when I add OH minus, that's going to react with H plus to form water, which decreases the concentration of H plus. Because it decreases the concentration of H plus, it's going to move toward that species, which means this equilibrium is going to shift left. Then if I were to add acid, I am increasing the amount of H plus ions in solution. So I'm increasing H plus, which means I'm going to shift away from that species and make more products. Again, you can also think about this just based off of the weak base and its conjugate acid. So if I add base, it's obviously going to react with the conjugate acid and form more reactants. If I add more acid, it's going to react with the weak base and form more products. Here are some common examples of buffer systems that you definitely should start to recognize. In each case, what makes them a buffer is that they contain a weak acid and its conjugate base, or a weak base and its conjugate acid. For example, the acetate buffer is made from acetic acid and acetate. The ammonium buffer is made from ammonium and ammonia. The fluoride buffer is made from hydrofluoric acid and fluoride ions. And the phosphate buffer is made up of H2PO4- and HPO4-2-. The key thing to notice is that each pair differs by exactly one hydrogen ion, and that's how you know they are conjugates and can function as a buffer. Just keep in mind that original has to either be a weak acid or a weak base. If it is strong, it is not going to form a buffer. Now, a common question that I get is, why is HF considered a weak acid? Because we know that fluorine is so strong. So kids kind of assume, well, HF should be a strong acid then. Well, because fluorine is so strong in electronegativity, the attachment that it forms with the hydrogen is actually quite strong. So because that bond between H and F is so strong, it's not going to dissociate very much in solution, which therefore does not make it a strong acid, makes it weak. All right, so let's do a couple buffer examples from College Board. This first one says a buffer solution is made up of acetic acid and sodium acetate. The major equilibria in the buffer system are represented above. Which of the following equilibria could be used to support the claim that an addition of a small amount of NaOH to the buffer will result in only a very small change in pH? So since sodium hydroxide is a strong base, when we add sodium hydroxide, what we're really looking at is the addition of OH minus. In a buffer, that added hydroxide is going to get neutralized by the weak acid component, and here that is acetic acid. So the equation that shows acetic acid neutralizing the hydroxide is going to be B, and we can see it's going to neutralize it into the conjugate base and water. The acid ionization equilibrium, or Ka, for HF is represented by the chemical equation above. A student claims that the pH of a solution that contains 0.1 molar hydrofluoric acid and 0.1 molar sodium fluoride will change only slightly when small amounts of acid or base are added. Which of the following pairs of equations can the student use to justify the claim? So we are looking for a reaction that shows the buffer neutralizing acid and another equation that shows the buffer neutralizing a base. So first, let's identify our weak acid and the conjugate base. We know our weak acid is going to be HF, and its conjugate is going to be F minus. So when we add base, that's going to be reacting with the HF. And when we add acid, that's going to be reacting with the F minus. So looking at A, we see that our weak acid is neutralizing the base, but in the second equation, we do not have the opposite occurring, so A would not be the correct answer. In B, we can see that our conjugate base is neutralizing added acid, so that would be a correct equation, but we do not have the opposite happening up here, so B would not be the correct answer. In C, we do have our weak acid neutralizing added base to form water and the conjugate base. However, in the second equation, our conjugate base is reacting with water, which is not neutralizing added acid, so that would not be the answer. D would in fact be the answer because we have our weak acid neutralizing added base to form water and the conjugate base. We also have our conjugate base reacting with acid to form our original weak acid of HF and water. So those both are showcasing that adding acid or base to this equilibrium is going to shift and offset that pH change. All right, now moving on into the Henderson-Hasselbalch equation, which is lesson 8.9, which connects everything we've learned about buffers to actually calculating pH. So remember, buffers resist change in pH when small amounts of acid or base are added. But now our goal is to be able to determine the pH of a buffer solution based on the identities and concentrations of the conjugate acid-base pair. So the key idea is that pH of a buffer is going to depend on two things: the pKa of the weak acid and the ratio of the conjugate base to the weak acid. This relationship comes directly from the equilibrium expression for a weak acid and is summarized by the Henderson-Hasselbalch equation. What's really important is that when small amounts of acid or base are added, the ratio of conjugate base to acid doesn't change very much. And because the ratio stays nearly constant, the pH also stays constant as well. And that's why buffers are so effective, because they keep the ratio of base to acid relatively stable, which keeps the pH stable. The Henderson-Hasselbalch equation is really useful because it allows us to quickly calculate the pH of a buffer without having to go through a full equilibrium ice table. And it's essentially based on the equilibrium between the weak acid and its conjugate base. And so what the equation tells us is that pH depends on the pKa of the weak acid and the ratio of the concentration of the conjugate base to the weak acid. So here is our Henderson-Hasselbalch equation, and that is on your formula sheet. You do not have to memorize it. You just have to know when to use it. And you will only be using it when you have a buffer. So please be sure to know when you have a buffer solution. And again, you can look for two things. Number one is that you have a conjugate acid-base pair, and number two is that that conjugate acid-base pair is from a weak acid or a weak base. All right, so let's do an example of how to use the Henderson-Hasselbalch equation. So this example says find the pH of a buffer with a 0.5 molar acetic acid mixed with 0.25 molar sodium acetate, and it gave us a Ka value. So I am looking to solve for pH, so I'm going to use the Henderson-Hasselbalch equation for a weak acid because that is what I'm given. I'm given a weak acid and I'm solving for pH. So we know pH is equal to the pKa. Well, I'm given Ka, and I know pKa is going to be equal to the negative log of Ka. So in your calculator, you can just do the negative log of 1.8 times 10 to the negative fifth. And that gives you 4.7447, and I'm just going to do a couple extra significant figures so I don't have rounding errors. Then the next part of the equation is plus the log of the concentration of our conjugate base over the concentration of our weak acid. Now I need to look at what values I'm given in order to solve for those two values. Now my weak acid is acetic acid, and I'm already given the concentration of that. So that's going to be 0.5 in the denominator. And then in the numerator, I'm looking for my conjugate base. I know my conjugate base is acetate, and there's only one acetate in here, so it's a 1-to-1 ratio, so I can use 0.25 molar in the numerator. And that gives you a pH of 4.44 for our buffer. Now let's look at what that all means with correlation to yesterday's lesson on 8.7. So I know that at the half equivalence point with a buffer solution, my pKa is equal to my pH. And at the half equivalence point, I have equal amounts of my weak acid and my conjugate base. So what that means is at a pH that's equal to my pKa, which is 4.74. So at a pH of 4.74, I have equal amounts of acetic acid, CH3COOH, and acetate, CH3COO-. However, looking at these concentrations of the buffer, you can see that I clearly have more acetic acid, which would be on the left side of the titration curves that we talked about yesterday. So when we're calculating with the Henderson-Hasselbalch equation, and you see that we clearly have more of our weak acid, you can expect a lower pH than you would at the half equivalence point. All right, another example says a student obtains 250 milliliters of a buffer containing 0.6 molar HF and 0.2 molar NaF. Calculate the pH of this buffer, and you are given the Ka value. So again, we're given Ka, and we are given a weak acid, so we are going to be solving with the top Henderson-Hasselbalch equation, where pH is equal to the pKa plus our log of the conjugate base over the weak acid. So first, let's start off with our pKa. Remember, pKa is just the negative log of our Ka value. So go ahead and plug that into your calculator. And that gives us a pKa of 3.14. Now, just a side note, before we solve this, I want to go back to what we learned about in 8.7. If at the half equivalence point, pH is equal to pKa, that means when the concentration of HF is equal to the concentration of its conjugate base, F minus, the pH is going to be 3.14. Now, in this problem, we can see we clearly have more HF, or more of our acid. So when we're solving using the Henderson-Hasselbalch equation, we should know that our pH is going to be lower than the pH at the half equivalence point. So we're looking for a pH below 3.14 when we're checking our math at the end. So now let's finish our Henderson-Hasselbalch. We have plus the log, and then it's going to be conjugate base over weak acid. So conjugate base is F minus, that is a 1-to-1 ratio here, so that's going to be 0.2, and then weak acid is HF, so that's going to be 0.6. And I hope you caught that mistake. It's supposed to be conjugate base over weak acid. I had it flipped. So conjugate base is our 0.2, and weak acid is our 0.6. So now go ahead and plug that into your calculator and solve for pH. And you get a pH of 2.67, which is in fact lower than our expected pH at the half equivalence point. So that does make sense. All right, now let's work through this titration problem. We're starting with acetic acid, which is a weak acid, and we're adding KOH, which is a strong base. We know that our H from the acid and our OH from the base is going to react to form water. And then we're going to be left with a salt, which in this case is going to be potassium acetate. Then remember, our KOH dissociates because it's a strong base, and potassium acetate dissociates because it is a soluble salt. So this would be our complete ionic equation, and then K plus or potassium ions are going to be our spectator ions. So when we're looking at our net ionic equation, we have our weak acid, which does not dissociate, plus hydroxide reacts to form water and acetate. And you don't have to do this every time, but I think it's important for identifying what's actually happening at the particle level. So with a titration, there's added levels of understanding in order to plug it into the Henderson-Hasselbalch equation. So I know that I have a buffer with acetic acid and acetate looking at my net ionic equation. And I know I'm trying to find the pH, and I know I have the Ka. So all of that information is pointing me towards this top Henderson-Hasselbalch equation for a weak acid. So if I'm trying to solve for pH, I know I need my pKa, and I already have my Ka. So I'm just going to take the negative log of the Ka so that I can have pKa. Now, to finish my Henderson-Hasselbalch equation, I have to have the concentration of my weak acid and the conjugate base. And that is where the understanding of the titration comes into play. So in order to figure out what is being neutralized, I first need to find out how many moles of my acid and my base that I have. So I know that concentration is equal to moles over liters, and I have volume and concentration for both of these substances, so I can rearrange this equation to moles equals molarity times liters to get moles of each. So for acetic acid, I have a concentration of 0.1, and I have 25 milliliters or 0.025 liters. So that's going to give me 0.0025 moles of acetic acid. And then doing the same thing for my potassium hydroxide, I'm going to get moles of that. So I want to multiply my concentration 0.1 times my volume, which is 10 milliliters. So that's going to be 0.01. And that's going to give me 0.001 moles of potassium hydroxide. And since I am following my net ionic equation, that is going to be equal to hydroxide. So everything in my net ionic equation is a 1-to-1 ratio. And if I'm looking at my two reactants, I know that my limiting reactant is going to be hydroxide because I have less of it. So this is going to be my limiting reactant. And because hydroxide is my limiting reactant, I know that all of the hydroxide reacted with equal amounts of acetic acid to form the same amount of my conjugate base. So that means in my buffer solution, I have 0.001 moles of acetate, and in order to get my concentration, I'm just going to be dividing that by the total volume. And my total volume is going to be 25 milliliters plus 10 milliliters, which is 35 milliliters. And I want to divide that by liters, so it's going to be 0.035 liters. And that's going to give me my concentration of my conjugate base, which is the numerator in the Henderson-Hasselbalch equation. Now we need to figure out our concentration of weak acid. So we know that we started out with 0.0025 moles of acetic acid. We also know that we used up 0.001 moles of acetic acid to neutralize all of our hydroxide. So if we take 0.0025 and subtract 0.001, that means we're left with 0.0015 moles of acetic acid left over in solution. So in order to get concentration of that, again, we're going to take the moles and we're going to divide it by the total volume, which we already found at 0.035 liters. And that is going to give us a concentration of acetic acid at 0.042857. So now that we have those two values, we can plug them into the Henderson-Hasselbalch equation and solve for pH. And before we write down that answer, I do want you to think about what we learned about in 8.7. At the half equivalence point, our pH should be 4.74, which means at a pH of 4.74, we have equal amounts of acetic acid and acetate. But clearly, we have more acetic acid in this buffer solution. So we should be expecting a pH lower than 4.74. And by plugging that into our calculator, we get a pH of 4.57, which does follow our idea from 8.7. All right, and because that one was so much fun, let's do another one, but with a base. So for this specific titration problem, we're going to be solving for POH because we're given KB and a weak base. So we're going to be solving for POH with the Henderson Hasselbalch equation for a weak base. And then since it's asking for pH, we're just going to take 14 minus the POH, and that's going to give us pH. All right, so let's first start with our equation. We have NH3 reacting with HCl, and that is going to form a salt, NH4Cl. So let's break that apart into a complete ionic equation. We know HCl is going to break apart because it's a strong acid and it completely dissociates, and NH4Cl is going to break apart because it is a soluble salt. So we're going to have NH3 sticking together because it is a weak base. Then HCl is going to dissociate because it is a strong acid. And then NH4Cl is going to dissociate because it's a soluble salt. And this is our complete ionic equation. Remember, the difference between complete and net is taking out your spectator ions. So our spectator ions in this specific example is chlorine ions. So then our net ionic equation would be ammonia plus H plus ions react to form ammonium. And again, you don't have to do this. I just think it helps with the understanding of everything. So now let's figure out what we need. We know we're solving for POH first. We need the pKb, and since we're given the Kb, we're just going to take the negative log of Kb, and that's going to give us pKb. And now to continue on with our Henderson-Hasselbalch, we have plus the log of the concentration of our conjugate acid over our weak base in terms of concentration. So now, using our values given, we're going to solve for the concentration of those two things. And remember, NH3 is our weak base, and NH4 plus is our conjugate acid. So remember, to see how much is neutralized, we need to get the moles of each. So since we are given volume and concentration, we can solve for moles by multiplying our concentration times our volume in liters. So for NH3, we have a concentration of 0.5 and a volume of 0.03 liters. And that gives us 0.015 moles of NH3. And now we need to figure out the moles of H+. And now, so we're going to get that from HCl. So again, to get moles, we take the concentration for HCl, which is 0.1, times the volume in liters. 10 milliliters is equal to 0.01 liters. So that's going to be 0.001 moles of H+. Now again, H+ is our limiting reactant here, which means we're going to run out of H plus when we use 0.001 moles. So that means we're only going to be using 0.001 moles of NH3, and that's going to produce 0.001 moles of our conjugate acid. So now that we know in this buffer solution we have 0.00 moles of our conjugate acid, we're just going to divide that by our total volume, and that will give us concentration for the numerator. So total volume is going to be 30 milliliters plus 10 milliliters, which is 40 milliliters, so 0.04 liters. And now we need to get our concentration of weak base, or NH3. So I know I started with 0.015 moles of NH3. Then I needed to use 0.001 of that to neutralize, which means in solution at the end, I have a remaining 0.014 moles of NH3. So if I want to calculate concentration, then I just take my moles, 0.014, and divide it by total volume, which is 0.04. And that gives me 0.35. So now that I have that information, I can go ahead and solve in the Henderson-Hasselbalch equation for POH. And I get 3.599 or 3.60. And so now that I have POH, all I do is subtract that from 14. So 14 minus 3.60 is going to give me a final pH of 10.40. All right, this example says a chemist needs to produce a buffer with a pH of 8. If he has access to a solution of 0.5 molar HClO, what concentration of NaClO should be used in the buffer? So this question is a little bit different in that we are not solving for pH, we're actually solving for a component within the Henderson-Hasselbalch equation. So we already have pH at a pH of 8. We also have the pKa by taking the negative log of our Ka. So in your calculator, do the negative log of 3 times 10 to the negative 8. That's going to give us a pKa of 7.5229. And then we have the log of the concentration of weak acid over the concentration of conjugate base, which is ClO minus. Now, we already have the concentration of our weak acid, which is 0.5. So that's going to go on the bottom. And we are solving for the concentration of conjugate base, which is X. So now let's figure out how could we solve this. Now, if you want to go ahead and plug this into your numerical solver, I kind of showed you down here how to do that on your calculator. If you would rather do it that way, you can also do it very simply algebraically. So first, take minus 7.5229 on both sides. That's going to give you 0.4771 equals the log of X over 0.5. Now to get rid of log, I know I need to take 10 to the power of that. So I'm also going to do 10 to the power of 0.4771. 10 to the 0.4771 is equal to 2.9999. That's going to be equal to X over 0.5. So then in order to get X, or my concentration of ClO minus, that is going to be 2.9999 times 0.5. That's going to give me 1.4999. And then looking at sig figs, it looks like my smallest is 2 sig figs. So my final answer is the concentration of ClO minus is going to be 1.5 molar. All right, a student prepares a lactic acid sodium lactate buffer solution by mixing 40 milliliters of 0.5 molar lactic acid with 200 milliliters of 1 molar sodium lactate. The pKa of lactic acid is 3.08. What is the pH of the resulting solution? So again, this should hint you towards Henderson Hasselbalch. Because we're solving for pH, we're given pKa, and we have clearly a buffer solution because it literally told us. So with these values up here, we can get the concentrations of our weak acid and conjugate base. So thinking back to Henderson Hasselbalch equation, it's pH equal to the pKa, which is 3.08, plus the log of the concentration of conjugate base over weak acid. So first let's solve for our conjugate base, which is lactate here. It's a 1-to-1 ratio, so we know that we can use our concentration and volume to get moles. So let's start there. So we're trying to get moles of lactate, CH3H5O3 minus. We're going to do that by taking concentration, which is 1, times the volume in liters, which is 0.2. So that's going to give us 0.2 moles. And then to get concentration, we need to divide it by total volume. So that's going to be 40 plus 200, or 0.24 liters. So 0.2 divided by 0.24 is going to give us 0.833 repeating. So that is our concentration of the conjugate base. So that's going to go in the numerator. So 0.8333 repeating. Now let's get our weak acid concentration. So same concept. We have moles of HC3H5O3. We have 0.5 molar solution with 40 milliliters, so 0.04 liters. So 0.5 times 0.04 is going to give us 0.02 divided by 0.24 liters. That gives us 0.083 repeating. So that's going to go in the denominator. So then we can go ahead and solve for pH. And that pH is going to give us 4.08, which is our answer. All right, the chemical equation above represents the acid ionization equilibrium for butanoic acid, which has a pKa of 4.8. Which of the following is the best estimate for the pH of a buffer prepared by mixing 100 milliliters of 0.2 molar butanoic acid with 100 milliliters of 0.1 molar sodium butanate? So looking at our relationship between the concentration of weak acid with conjugate base, that's going to tell us what is the relationship between that and the pKa. Because we know at the pKa, which is the half equivalence point, our pH is going to be equal to 4.8. So that means that when our concentration of butanoic acid is equal to our concentration of butanoate, C4H7O2 minus, our pH is going to be 4.8. Now, looking at our moles of each, we can see that we have an excess of our weak acid. And we know if we have an excess of weak acid, that means we're going to have a lower pH than we would at the half equivalence point. So we're looking for a pH slightly lower than 4.8. So our answer would be B, 4.5. So just to summarize, if the concentration of the acid and the base in the buffer were the same, the pH would be equal to the pKa, which is 4.8. However, the concentration of the weak acid is higher than the concentration of the conjugate base, and therefore the pH will be slightly lower than the pKa. All right, and last question for this slide. The table shows the values of Ka for 4 weak acids. Which of the following pairs of chemical species, when combined in equal molar amounts, results in a buffer with a pH closest to 7.5? So first I want to go over the Henderson-Hasselbalch equation quickly. Now, what happens if our concentrations are the same? That means we would have log of 1. And if you plug log of 1 in your calculator, you end up getting 0. Which means if our concentrations of weak acid and conjugate base are the same, that means that the pH is equal to the pKa. So if we're looking for a pH of 7.5 and they're equal molar amounts, then we're looking for a Ka that the negative log of it is going to give us a value closest to 7.5. And when we get the pKa's of all of our acids, we can see that HClO produces a pKa that is equal to the pH. So the answer for this question would be C.